Okay, so now that we know all about work and we know how to use a scalar product, we're now going to have to look at how work can be related to kinetic energy. So if we look at problems with forces, we did fairly simple problems when we did chapter 5 and 6. Forces, though, can be very complicated, and problems can be extremely hard to solve using forces, particularly with the breaking of the forces up into the various vectors and their components. So what we're going to do is we're going to be able to relate the work directly to the speed or the motion. And yes, we'll have to know a little bit about the forces, but not the detail needed to use the force problems that we had where you had to go get the acceleration and make it a very tedious process. So that's what we're going to do in the next part. So what we'll do is we'll start by just looking at an object that's being moved forward by just some net force. So I have a mass M, and it's being moved along a straight path. We can pretend that my path here is straight. So whatever it is, there's some net force that's moving this thing forward. Okay. And again, that net force, therefore, we know it's going to accelerate. So then if that's the case, again, we know that we have some distance that'll move, delta S. And what I want to know is, or what I do know is that here, when this is moving, here I have some initial velocity VI. And I'm going to call that VI equal to just V naught. And here, the box, the mass M, has some VF, which we'll just call V. Okay. So this is the system that we're looking at. Now, let's define what some of these terms are. So the net force that we have here is some constant net force, and that's going to cause the object to accelerate with some constant acceleration A. Now, at some point, we will look at something where the force is not constant, particularly we'll look at springs. But for now, we're just looking at constant forces that cause a constant acceleration. So now we're going to define the work due to this net force. All right, that'll be W net. That's the work done by this force F net. So we're not looking at what makes up that net force. We're just saying that there is work done by this net force. So now I just want to work out the mathematics. W net, we know that'll be the F net, the force F net, dotted with the displacement delta S. Okay. Well, again, by definition, because it's a dot product, I have F net delta S times the cosine of phi, the angle between them. Well, if I look at these two forces, what do I have? Well, I have F net going this way. And I know that delta S is always going that way as well. So I know here that phi is just going to be 0 degrees. They're both going the same direction, which means that the cosine of 0 degrees is just going to be 1. So knowing that that's the case, then I can say that W net is simply going to be F net times delta S. So far, so good. That looks fairly simple. But what else do I know here? Well, I know what F net is. I know from what I've defined before that F net is equal to the mass of the object times A, right? And again, I'm just looking at the magnitude. So in knowing that that's the case, then I can say that W net is going to equal MA times delta S. So we have this definition, and that's going to help us on the next step of the problem. Now, I just want to reiterate something that we stated before, but just to make it clear, we know that A is going to be a constant because, why? Because F net is a constant, right? For a constant force, mass isn't changing. We don't have some weird nuclear thing going on here, right? So we know, therefore, that basically my A is going to be constant. So that's because my F is constant. And I can also say that delta S is the same as delta X, right? delta x, and I probably could have used a delta x in the beginning. It's the same thing. Okay. So then when I use that and I put that in there, I know that W net equals M times A delta X. Well, this A delta X is something that should seem familiar to you, right? So what I want you to do is go back into your memory banks and recall that when we dealt with kinematic motion, we had a formula that said V squared equals V naught squared plus 2A x minus x naught. Well, x minus x naught, this thing here, if we look at it, that's just equal to delta x. All right. So we can rewrite that formula. We can say that V squared equals V naught squared plus 2A delta x. Well, we can say that 2A delta x is going to equal V squared minus V naught squared. And then we can say that A delta x is just going to be 1/2 V squared minus V naught squared, or 1/2 V squared minus 1/2 V naught squared. Now you might think to yourself, okay, well, what do I do with that? Well, I'm going to take that and I'm going to plug it in for my expression for delta S. So again, W net is M times A delta X, right? And that's just M times 1/2 V squared minus 1/2 V naught squared. Well, let's just put that through every term. And we have this great expression. We have that the network is equal to 1/2 M V squared minus 1/2 M V naught squared. And this is the expression that I just derived that relates the work directly to the motion being V squared is its final velocity, and V naught squared is its initial velocity. So that's pretty neat because it tells me that my work can be related to these things, right? Regardless of what caused that net force. If there's a net force and it's constant, I don't need to know the force. I just need to know its starting and stopping velocity. And of course, this equation has consequences to it. So what we're going to do is look more closely and see how this actually gives us kinetic energy. So as we said before earlier in previous set of slides, when we first talked about energy, we said we were going to look at mechanical energy. Mechanical energy had kinetic and potential. So kinetic energy, again, was just the energy associated with motion. Well, if you look at the expression we derived, W net is 1/2 M V squared minus 1/2 M V naught squared. Well, look what I have here. I have this term, this 1/2 mv squared. And really, you could write that as 1/2 mvf squared minus 1/2 mvi squared, right? Either way, you need a velocity at two different points of the object's motion. So this is where we're going to define our kinetic energy. K is going to be kinetic energy, right? So we don't have to keep writing kinetic energy out. What I'm going to say is K is going to be 1/2 mv squared, okay? So I'm going to call kinetic energy 1/2 mv squared. Now, before I do that, let's make sure my units work out, right? Because W net and kinetic energy, right? They're both energy. Work is energy. So I should get the same units of energy for kinetic energy if I'm correct in my analysis here. So what we're going to do is check the energy. We're going to check the units of the energy. So when I check the units, what do I find? Well, I find that this K is equal to 1/2 mv squared. Well, a constant just has a unit of 1. Mass is a kilogram. V is a meter per second, and we're squaring that, right? So what do I have there? I have a kilogram meter squared per second squared, but I can divide this up into a kilogram meter per second squared times a meter. And again, a kilogram meter per second squared, that's just a Newton per meter. Oh, look, it's equal to a joule. So therefore, kinetic energy must also have units of joules, which means that your kinetic energy and work are both types of energy. So we now have the formula K is equal to 1/2 mv squared. So now we have an equation that'll give us the kinetic energy, the energy associated with motion. We'll go on to get the potential energy, but first we want to work with this a little bit because it's related to the work. So again, what do I find here? I find that W net is equal to 1/2 mvf squared minus 1/2 mvi squared. Well, what's that equal to? That's just kf, your final kinetic energy, minus ki, your initial kinetic energy. One can say that that's just the change in kinetic energy delta K. So what this does is this leads us to something called the Work-Kinetic Energy Theorem. And this is a theorem that you will use to analyze problems in physics. What it says is the net work done on an object by a net force acting on it is equal to the change in the kinetic energy of the object. Okay. And again, that theorem is just given by W net equals delta K, which is Kf minus Ki, using our definition of kinetic energy. So, can I define kinetic energy based on work? Absolutely. I could say kinetic energy is equal to 1, the total work done by a net force to accelerate a particle from rest to its current speed, or you can say it's the total work done by a particle in the process of coming to rest. So in one case, we look at it where the force is doing the work. On the other case, we look at it where the particle is doing the work. And really the force is doing the work, but whatever's applying the force is doing the work. But it's the same thing. The reason you do it for rest is we're looking at a single kinetic energy. So if your K is something and there's just 0 there, right? It's the work done to get from 0 to this value. So you can see that that's a wordy definition that you can use. However, We don't necessarily need to use that definition because we're just going to deal with doing problems and using that formula in red. So what we're going to do now is do a couple example problems that show you how to use this formula and determine some things about the motion of the particles or the objects. So when we'll look at the problem of the tractor we did in the previous section on work. So that tractor, it had done a total work of 10,000 joules pulling this sled full of firewood. So we got the total, the net work, by combining the work done by all the forces. The sled and wood had a total weight of 14,700 newtons. If its initial speed was 2 meters per second, what is the final speed of the tractor? Well, we know that W net is going to be 10,000. Again, we got that in a previous problem. And we also know that W net is equal to delta K, which is KF minus KI, which is equal to 1/2 mVF squared minus 1/2 mVI squared. So since that's the case, what I need to get the mass. All right, so I need the mass of the load. Well, you know that the weight is equal to mg, which is 14,700 newtons, right? So if that's the case, you know that the mass will simply be 14,700 divided by g, which is 14,700 divided by 9.81, which is going to equal 1,500 kilograms. So now that we have that, what we can then get is the kinetic energy initially and finally, right? So we know that Ki will be 1/2 mVI squared. Well, that's 1/2 times 1,500 times, we said VI was 2. So that's 2 squared. Well, when you multiply that out, that's going to be equal to 3,000 joules. All right. So I'm going to write off to the side what we have just so it's clear, right? We know W net, 10,000 joules. I think that's a good way to do these problems. We know that Ki is going to be 3,000 joules. Okay. So now what do we have left? We have to get the final. Well, K final is going to be 1/2 mVF squared, right? And that's going to be 1/2 times 1,500 times just VF squared. We don't know what that is. So we can write that over here. KF is 1/2 of 1,500 is going to be equal to 750. So I'll write that over here. The reason I like to do this is because then if I have all the pieces to my W net, I know that W net is equal to KF minus KI, right? And I have all these pieces. So just plugging what I know, I can say that 10,000 is equal to 750 VF squared minus 3,000, right? Which means that 750 VF squared is equal to 10,000 plus 3,000, which is 13,000. Okay. And then I can say that VF squared is equal to 13,000 divided by 750. Right? And that's equal to 17.3. Now I want VF, I don't want VF squared. So if VF squared is equal to 17.3, VF will be the square root of 17.3. And that's going to be 4.16. And there's my answer. I know that the final speed of the tractor, after it's pulled it after it's done that amount of work, rather. I don't remember what it was pulled. I think maybe it was 20 meters or whatever. That's my final speed. See how easy that was? I didn't have to do the force. I didn't really have to know the acceleration, right? I just had these scalar pieces and I put them together. And when I put them together, I was able to solve the problem. So these are so much fun. Let's try another one. Okay, so here's a little bit more complicated problem. In a pile driver, a steel hammerhead with mass 200 kilograms is lifted 3 meters above the top of a vertical I-beam. The hammer's dropped, driving the beam 7.4 centimeters further into the ground. Again, having a lot of time in the city, this is what they use to take these giant steel beams and just drive them into the ground. They take this huge, it's called a hammerhead, but it looks like a big block of steel. And they lift it up and they drop it and it hits the beam, driving it in the ground, lifts it up, drops it, hits it, and drives the beam into the ground. This is how you do a lot of things when you're driving things into the ground for foundations, or, even for like, when you're starting with skyscrapers, at some point you need this to dig into the ground so that your beam sits and rests in the ground. So there's a frictional force of 60 newtons on the hammer. We're going to use the Work-Kinetic Energy Theorem to find the following. First, we'll find the speed of the hammerhead just as it hits the I-beam. Then what we'll do is we'll find the average force the hammerhead exerts on the I-beam itself. So let's start by drawing a diagram. And in this case, in our diagram, we have a mass. That mass is the hammerhead. And that mass is going to fall and move. Okay. So it falls 3 meters. All right. So it's moving that way. So we know that the distance it's moving, call it delta y. Okay. This distance, delta y, is equal to 3 meters. All right. Because then when this thing falls, it hits the beam, which would be resting here. Okay. We know at the top that vi is going to be 0. You start it from rest, and then you drop it. So you have v is equal to, who knows? That's what we're trying to figure out. And so what we need to do is let's do a quick force diagram on this puppy, just to see what forces are acting on it. Well, they told us that, of course, there's mg going down. That's due to gravity. And they did tell us that there's a frictional force equal to 60 newtons going up. But that's it. There are no more forces on that. So what we want to do now is we want to get the net work, because if we get the net work, then we can use the Work-Kinetic Energy Theorem to figure out how far it's going when it hits the beam. So we have two forces. So first of all, let's write our forces out. There's gravity and then there's friction. Let's get gravity first. I'm going to use red. So the work due to gravity is just the force of gravity dotted with the delta y, the distance that you're falling, right? Well, that's just going to be mg, that's what gravity is, delta y times the cosine of the angle between them, okay? Well, let's draw the angle between them. Well, I have mg going down, and I also have delta y going down, right? Because that's the direction it's moving. So phi is going to be 0 degrees, okay? So knowing that that's the case, I know that the work due to gravity is going to be mg, and actually let's plug in what we got. So I know m is 200, that's the mass given. G is 9.81, okay. I know delta y is 3 meters, and I know it's the cosine of 0 degrees, which is just 1. So when you multiply that all out, what do you get? 5,880 joules. That's the work done when having that block fall. That's what the block does to fall, right? It does that work. It does that work against gravity. So let me write this down here. The work due to gravity, 5,880 joules. We'll just put that off to the side. Now let's get the work due to friction. Okay, that's going to be the force of friction dotted with delta y, right? That's going to be force of friction, delta y, cosine of phi. You can see how this gets repetitive, and hopefully you guys get the gist of it after a while, right? So we know friction is going this way, and we know that delta y, of course, is that way. So what we know is that phi is going to be 180 degrees, right? One's going up, one's going down. So that means that the cosine of phi, which is the cosine of 180 degrees, that's equal to -1. So once I have that, I can then get my work due to friction. So that's going to be, they tell me friction is 60, delta y is 3, and -1. So the work due to friction is -180 joules. So I'm going to put that off to the side because that's another useful piece. And I like to put my useful pieces off to the side while I work these problems. All right, well, I need W net. So W net is going to be, again, the sum of all the works. That's just the work due to gravity plus the work due to friction. That's going to be 5,880 minus 180. So that becomes 5,700 joules. So I'm going to box that. My net work is 5,700 joules. So now what I'm going to do is I'm going to use the work-kinetic energy theorem, right? W net is delta K, which is Kf minus Ki. Well, Kf is what I don't know, right? I'm going to need that, but it's 1/2 m times Vf squared. That's 1/2 times 200 times Vf squared. So it's 100 Vf squared. So I'm going to box that, right? Now we know what Ki is. Ki is 1/2 m Vi squared, but that's 1/2 times 200 times 0. That's just 0 joules. So we know because it's at rest, you don't even have to worry about Ki, it just goes away. So once I have this now, I have W net is just Kf minus Ki. That's going to be 5,700 is equal to 180 Vf squared minus 0. So I have 180 Vf squared is equal to 5,700. So Vf squared is equal to 5,700 divided by 180. When I multiply that out, that's basically equal to, oh, it's not 188. My apologies. It's not 180, it's 100. I miswrote that. Let's just fix it quick, because that will throw our answer off and then I won't know why, right? So that's 100 Vf squared in the box. It's 100 Vf squared. So 100 Vf squared. Okay, so I fixed it. So I divide by 100, basically I get 57. Vf squared is 57. Well, I don't want Vf squared, I want Vf, which is the square root of 57, which is going to be 7.55 meters per second. So this is all part A, by the way. All right. So for part A, I know Vf of the pile driver is 7.55 meters per second. That's how fast the pile driver will be traveling when it's dropped 3 meters above, right before it hits the beam. So now what I'm going to do is let's go on and work with part B. We have these answers. Let's see if we can get part B. All right, so for part B, what we want to do is we want to look at when the hammerhead is driving the beam into the ground. Okay, so what do we have when that happens? Well, basically, you have, let me do a force diagram here. You have still the mass of the hammerhead, but the instant that it hits the steel beam, now what you have is you have a frictional force going up, and you have the normal force of contact that's due to it hitting the beam. Now, I drew the force diagram before I drew what happened. What actually is going on is you're taking this beam and you're driving it. You're taking this hammerhead and you're moving it because you're going to drive this beam. And you're touching the beam when this happens, right? But what you're going to get here is you're going to get a delta y, which is going to equal 7.4 centimeters, right? Because that's how far you're driving the beam in. And that's equal to 0.074 meters. You got to put everything in meters. Okay. We also know that at the top, we know what V is from part A. The instant that it hits, right? We know that up here, VI is going to be 7.55 meters per second. And we know that down here, you're going to have V equals 0. VF is going to be 0 because it comes to rest, right? It stops, so you don't have to worry about that. So now we're going to do the same process, but now we have to do it for a different set of circumstances. Now, I want to just point out is this Fn. Okay, what that is that's the force of the beam on the hammerhead as it drives the beam into the ground. Okay, so that's part of what we have here. Right? Force on the beam due to the hammerhead. Okay, there's another way to look at it. On the beam due to the hammerhead. Now, how do I know that? Because Newton's law, equal and opposite, right? If the hammerhead is putting a force on the beam has to put a force on the hammerhead, right? So the two are the same due to Newton's third. So now what we have to do is we're going to do the same thing we did before, right? We'll start by getting the forces. So we have WG, and that's going to be, again, the force of gravity dotted with delta Y. That's FG, and actually let me write down what it is, it's MG. Delta Y, cosine of phi. But again, if we're looking at it, it's not going to be any different than it was before, right? I have mg going down, and I'm moving down delta y. So I get that phi is equal to 0 degrees. Cosine of 0 degrees is 1. So when I work this out, I get the work due to gravity is going to be still 200 times 9.81, but what has changed now is my distance is 0.074. So that's the only difference, and then multiplied by 1. So that's equal to 145.04 joules, okay? Again, I'm going to write that down. The work of gravity is 145.04 joules. Let's box that just so I have it. Now, let's do the work due to friction because we've done that before. The work due to friction is going to be, again, the force of friction dotted with delta y. Oh, that's a terrible delta. That's going to be Fk delta y cosine phi. But now here we have something that's the opposite, right? We have delta y going down, but we have Fk going up, right? Because it's friction from the rails where it's moving on. So phi is 180 degrees. The cosine of 180 degrees is -1. So if I go do this, I got the work due to friction is going to be, it's still going to be 60. Delta y is now going to be 0.074. And you have -1. So when you work that out, that's -4.44 joules. So the work due to friction is -4.44 joules. Write that down off to the side. Now, if we do the work, I'm just going to move over here. If we do the work, do the normal force. That's going to be the normal force dotted with delta y. That'll just be the magnitude of the normal force, delta y, the cosine of phi. But now I have the same thing as I do with friction, right? Delta y goes down, but my normal force is going up. So again, phi is going to be 180 degrees. The cosine of 180 degrees is going to be 1. So putting that in, I get the work due to the normal force. That's going to equal Fn, I think I did my n backwards, times 0.074 times -1. But now I don't have the normal force. But however, I'll be able to use the Work-Kinetic Energy Theorem to solve for it. So it's -0.074 Fn. So now I'll write that down. Okay, so I have this off to the side so I can use it when I need it. So now what I want to do is I want to get the total work, W net. So W net is going to be the work due to gravity plus the work due to friction plus the work due to the normal force. So add them together. Well, I have 145.04 minus 4.44 minus 0.074 Fn, right? When I add that together, I basically get 140.6. Now, how did I get that to make sure I'm correct here? It should be equal to, oh yeah, it's 140.6, right? Minus 0.074 Fn. So that's my W net. Let me write that down. 140.6 minus 0.074 Fn. So here in this case, I don't have a number for F net. I have an expression where I need the normal force, but I'm solving for the normal force. So we know that W net is equal to Kf minus Ki. Okay. Well, I know that that's equal to 1/2 mvf squared minus 1/2 mvi squared. Well, I know what vf and vi are, right? So I know that's going to be 1/2 times 200 times 0 squared, because its final velocity is 0. And that's going to be minus 1/2 times 200, 7.55 squared. So when I work that out, that's equal to 0 minus 5,700, which is -5,700 joules. So look what I got here. I have another expression for FW net, -5,700 joules. Well, in this case, when I have an expression where two things are equal, what do? I put them together. So I have -5,700 joules. I don't need the joule sign. That's going to equal 140.6 minus 0.074 Fn. Let's rearrange this. I have 0.074 Fn. That's going to be 140.6 plus 5,700. Add that together, that's 5,840.6. So So then I have Fn is equal to 5,840.6 divided by 0.074. When I work that number out, that's 78,900 newtons. That, my friends, is a large force, right? So you can see why that steel hammerhead is successful in driving in the beams. There you go. So 78,900 is the answer. So that's how we do that problem. Okay, well, didn't mean to do that. Let's go on to our next page, because now we want to start looking at what happens if you have a varying force. So we're going to look at work and energy of varying forces. So until now, to this point, F has been a constant force. We said that a constant force with a constant acceleration. But the question lies, what's going to happen when it's not? Well, let's graphically take a look at forces that are constant. Now, there's two ways they have to be constant. Number one, of course, they're going to be constant over time. Okay. So if I pick two times, T1 and T2, and I graph my forces, right, I would expect over time that a constant force will basically be just that. It'll stay constant over time, making a square and having some value, just call it F naught. Now, the other way I have to look at it is I have to look at it as F changing over space, right? So in this case, if I have a force and I'm looking at it from x1 to x2, right? So the object's moving, I'm looking at that force, right? And again, let's call that F naught. But what we'll notice is the same thing. It'll be constant as it moves from x1 to x2, right? And again, we have an area kind of forms this rectangle. We'll just remember, right? Recall. We said that work was equal to F dot delta X. Okay. And if that's the case, assume F and delta X are the same direction. And if that's the case, what you would basically say then is that W is equal to F times delta X. Well, look what I have here. If we look at our rectangle, right, this here is delta X. That here is F, right? You go from 0 to whatever value you have, the F naught in this case. So what you can say is that work is going to equal the area under the F versus X curve. Now it turns out that this is true not just for nice rectangles, but for any force in an F versus X graph. So now we have a powerful tool here. So what you would do, this is where your calculus is going to come into play. Let's suppose I have F versus X. I have an F versus X curve. And then let's suppose I have some force. Kind of looks like this. Okay. let's suppose that I'm interested in what's going on with this force. And we'll go from here, which will be some x1, to here, right? Which will be some x2. Now, how do I find the area of the curve? Well, what you do is you divide it into little rectangles. And I'm not very good at drawing rectangles, but you get the gist. And of course, what you're doing is, this is the process of integration, right? Where you would take one of these little rectangles and know that that's delta x. And so the work is going to be the limit as delta x goes to 0 of the sum of f times delta x, right? You're adding up all little pieces of force as you go. And again, that's equal to the area under the f versus x curve. All right, well, you know what this is. This is an integral. Using a Riemann sum, we're getting the area under the curve. So what you can say is the work, if you have something that changes with x, is simply the integral from x1 to x2 of f of x dx. And again, that's equal to, by definition, the area under the f versus x curve. So here you go. We're using that integration stuff that you learned in calculus. Okay. So what you would do then, and again, this is just for one dimension that we're going to do this in. Let me write that. When you get to mechanics, well, you might not get to mechanics ever, but in mechanics and upper level physics, what you would do is you would use this same idea, but you would do it in 2 and 3 dimensions. And that would also be a way to give you the work. We're just going to do one dimension. So W is equal to the integral from xi to xf of f of x dx, right? And again, that's the area under the f versus x curve. And so basically what you can say because of this is that W total is equal to the integral from xi to xf of f total of x dx. That's equal to delta k, which is equal to kf minus ki. So your work is still equal to your total work is still equal to the change in kinetic energy. It's just for variable forces, you have to integrate to get it. So here's an example. So calculate W for a constant force f of x just equals some value f. Now we know the answer, right? But I'm going to show you what it is because it's good to know where some of these things come from, right? There should be more than one way to derive something. Well, we know that work is equal to the integral from xi to xf, f of x dx, right? There's our integral. Well, I know that f of x is a constant. So it's just f dx, which I know I can pull out of the integral because you can pull all constants out of an integral. So it's xi to xf of dx. And we know the integral of dx is just x, right? So it's f times x evaluated from xi to xf. That's f times xf minus xi, which is just f delta x. And there's your answer. Cool the way that works, right? The work is equal to F delta X for this example of a constant force. Well, what I want to do is let's mix up a little bit. Let's try a force that's not constant. Let's try a spring force. So let me draw a line here. And so for this example, get the work done when using a spring force. Now, the spring force is F of X is negative KX. That's the definition of a spring force. That's called Hooke's law. So let me just write that out a little bit here. So F of X equals negative KX. That's the force of a spring acting on a mass. What is K? K is the stiffness of the spring. That's what that represents. We'll learn more about this because we're going to do a quick chapter on spring motion after we're done with momentum. And X is the position from natural equilibrium. And the spring is at its natural resting length. So if you didn't push or pull the spring, where would it sit before you apply any pressure, right? So what we're going to do is we're going to find the work required to stretch the spring. And that's what we're going to be doing. So let me do a diagram. We'll go to the next page. So if we're doing that, right, we have our spring and we're just going to do a horizontal spring that's resting on the ground. So when you first have your spring, right, it's attached to something near the wall and it just kind of sits there, right? That's M. Well, what happens is when you pull the spring, you're stretching it. What's going on with the spring? Well, the force of the pull is this way. But then what happens is the spring pulls back. So the spring is always resisting the motion. Okay. So what you find in this case is that your force pulling the mass will equal a force of the spring pulling against you in the opposite direction. Erase that. Sometimes the button gets stuck. So basically, if you have this mass, what's going on is, I'll do it over here, I guess. F of the pull is going to be KX, where here you'll have F of the spring is negative kx, right? So it's the same value, it's just the opposite direction. Newton's third. So that should be pretty self-explanatory. Okay, well, that just sets up what the problem looks like. What we're going to do is I have the work is going to equal, you're going to go from xi to xf, f of x dx. So let's plug in what my force is. It's kx, right? xi, xf, kx, dx. Oh, I can do the k just a constant, right? So I can pull the k out of the integral, xi to xf. It gives me x dx. Okay. What's that integral? Well, you should have learned that in calculus, but that integral is x squared over 2, evaluated from xi to xf. And that's going to be k times 1/2 xf squared minus 1/2 xi squared. Now, in the problem that I gave you, if the spring starts at equilibrium, then xi is equal to 0, right? Because the x value is your distance from equilibrium. So if you're starting at equilibrium, right, that's just 0. So what I would do is putting that in there, I get work is equal to 1/2 k xf squared. And that would be the answer to that problem. So we can say this in better terms, right? We can say that the work equals 1/2 kx squared. What does that mean? That's the work done by a person pulling the spring and stretching it some distance x from equilibrium. Okay, and that's what we got from this problem here. Well, there's another way to do it too, right? So we know that graphically, we can do this graphically. What do you mean graphically? Well, graphically, what I mean is I'm going to draw the force on the graph, right? So we'll start at rest. At equilibrium, we'll go to here, right? And this value will occur at x. And this here is f equals kx, right? And again, this is my f, and this is my x. Well, what do I know? I know the work is the area of the curve, right? So let's solve it that way. Work is the area under the f versus x curve. Well, that's going to be equal to area of a triangle, 1/2 base times height. All right, well, the base is going to be x, right? And this, of course, will be kx. Look what I get, 1/2 kx squared. So I get the same answer solving it graphically as I do integrating. So there you go, 2 methods, and basically that's going to be the work that's done on a spring. So let's do a quick problem. which will help us dealing with the spring. Okay, so we have a woman that weighs 600 newtons and she steps on a scale. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the constant of the spring and the total work done on it when it is compressed. So the first thing that we want to do is we want to draw what this might look like. So basically, if I have a scale is a spring. And so basically you have this spring that's here that's used, and when it's compressed, based on how far it's compressed, they can determine what your weight is, right? So now this will have a mass on it. Okay. Now, without the mass, the spring would be up here, right? So the spring has been compressed a little bit because of the mass, right? That makes sense. So the distance is going to be negative 1.0 centimeters, which I'm going to say is negative 0.01 meters. Okay, just because we have to have that. Now, this spot up here is equilibrium. So when you're compressed from your equilibrium position. All right. So basically, what do we know? We know that X is equal to negative 0.01 meters, right? That's the compression. So now let's look at the spring and see how we can possibly get the spring constant. Well, we know again that if we do a force diagram on the spring, so this is the spring, we know that there's a force pushing it down of 600 newtons. 600 newtons is pushing that spring down, right? So we know that F of the spring is equal to Kx, which is going to equal 600 newtons. And that'll be negative 600 newtons because it's going down. Okay. So basically you have F of the spring, Control Z, sorry. You know that in this case, you know that X will be negative 600. Oops. Let's say K is negative 600 over X, right? That's negative 600 or 0.01 negative. Look, the negatives cancel. So K is just 600 over 0.01. What's that going to be? That's going to be 60,000 newtons per meter, because that's what it is. It's a force over a meter, newtons per meter. So there you have the K of the spring. 60,000 newtons per meter. Okay. Now, once you have that information, you can very easily get the work. It's 1/2 Kx squared. So it's 1/2 of 60,000 times 0.01 squared. That's equal to 3 joules. So the work done in compressing that spring, when you're using the scale to take a measurement, is 3 joules. Okay. So I want to go on and just show you a small calculus thing, just because I think it's fun. So this is not something you have to know, but I think it's something that's kind of neat to understand. And I think that, I don't know, you might enjoy just seeing how it works. Actually, before I do that, let me give you one last example problem, and then we'll go on and show you the neat calculus application. So let me write the problem down. Okay, so we have an air track glider of mass, 0.10 kilograms, and it's attached to the end of the air track with a spring. The spring has this force constant of 20 newtons per meter. Now, initially, the spring is at equilibrium, and when it's at equilibrium, it's moving 1.5 meters per second to the right. Find the maximum distance it will move if there is no spring. So what we need to do is find how far it's going to move. So let's draw a picture of what's going on. So basically, I'll draw it over here. We have a spring that initially it's at equilibrium, right? So we know this is x equals 0. But it's moving this way at v equals 1.50 meters per second. Well, then what's going to happen is it stretches, right? Right. And at this point, it stretches to its maximum. So what we don't know is the distance of this thing. So we can say that at this point here, it's just some distance d, right? So then here, xf is going to be d. What happens when you stretch something? Well, when it's stretched to the max, v is going to be 0. And we'll talk about that in a little bit, but it's much like a baseball that goes up and stops and then comes down. Okay, because it has to stop and turn around. Well, that's what's going on here. It has to stop and turn around. So let's start by getting F net, or W net rather. We know that W net is going to be 1/2 k x squared. This is part A, so there's no friction. So now what we know is W net is just equal to, and let me back that up a little bit, equals W of the spring, which is 1/2 k x squared. And I said that's equal to D, and we know what K is, so that's 1/2 times 20 is what K is, D squared. So I just have 10 D squared. So what I can do is just off to the side, W net will be 10 D squared. Okay. What we know is now, this is not W of the spring. This is actually W net is the force, right? What I have to note is the spring pulls opposite of the motion, right? So what I need to say is that, make a note of this in green, spring pulls opposite of the motion. So its work is negative. Now, I didn't actually plug in what it was, but how would I know that? Well, because I know if I'm looking here, right, I know I'm moving this way, D, but F of the spring is this way, right? And I know that the angle between these is 180 degrees. And I know that the cosine of 180 degrees is -1. So therefore, I know that W of the spring has to be -10D squared, okay? So what I should say is W net is going to be the magnitude of that, okay? So let me write this down here. W of the spring, -10D squared, okay? Now, once I have that, the rest is pretty easy, right? If I want Ki, I know that's 1/2 mvi squared, okay? That's 1/2, the mass of the spring is 0.100, vi is 1.5 squared, and I work that out, it's 0.1125 joules. So let me write this over here, Ki is 0.1125 joules. there's that answer. Kf is 1/2 m Vf squared. Okay, now what I need to know is that Vf is going to be 0, and I said that before, because why? Because at maximum stretch, the cart is stopped so it can turn around and move back toward the center, right? It gets pulled, it stretches, but it wants to go back that way. So it stops and turns around. So what we can say is that Kf is just going to be 0 joules. Okay. Well, what we have is W net equals Kf minus Ki. So I have negative 10d squared equals 0 minus 0.1125. I know that 10d squared, 0.1125. I know that d squared is going to be 0.1125 divided by 10. And that's going to be 0.01125. But I don't want d squared, I want d. The square root of 0.01125. And when you work that out, that's 0.106 meters. So the spring basically will stretch 0.106 meters when there's no friction. So that's part A's answer. Double box it. Now we have to go on to part B, which is going to include the friction. So when I do that, part B, the work net now will equal the work of the spring plus the work due to friction. We know the work due to the spring is negative. Plus, we have to include the work of friction. Now, we also know that basically Kf is still going to equal 0 joules. And Ki is going to be 0.1125 joules, right? These aren't going to change because I'm the starting and stopping speed. I'm just changing how far it'll stretch. Well, what I have to do is look at the work due to friction. So again, what's going on is, if you look at the picture, right, I basically have the mass moving this way, delta x, right? And I have friction that's pulling this way, Fk. And again, we have this angle of 180 degrees. And the cosine of 180 degrees is going to be -1. So why is that important? Well, because I get the work due to friction. I'm not going to keep writing it. I'm just going to have Wf. That's going to be the force of friction with delta x, right? That's Fk delta x. The cosine of 180 degrees. And that's just going to be negative Fk delta x. Now, what is delta x, right? Delta x is equal to d, which is the stretch of the spring. This is a piece that wasn't there before, so we need that. All right. Well, we have the work due to friction is negative Fk times d, but what is Fk? Well, Fk is equal to mu k times Fn. And in this case, right, if we do a quick diagram of the mass over here, we have mg going down and Fn going up, right? And the sum of the forces in the y direction, Fn minus mg equals may, but that equals 0. It's not moving up and down. It's just moving left and right, okay? So we can say that Fn is equal to mg. So then if I go back here, Fk is going to be mu k times m times g. Well, we know that's 0.47 times 0.100 times g is 9.81. Right, and that's equal to 0.4606. Well, let's plug it in. Then we know we have the work due to friction is going to be negative 0.4606 D. And there's the expression. So I have to tack that on. So I know W net is going to equal negative 10D squared plus the work due to friction. That's negative 10D squared minus 0.4606 D. Okay, well, I know again that that's going to equal Kf minus Ki, which is 0 minus 0.1125. So I get negative 10D squared minus 0.4606 D is negative 0.1125. Well, now what we want to do is we want to change that around a little bit and make it so that it's a little bit better, right? So what I'm going to do is I'm going to make it a positive. I'm going to bring this over and make it positive. So basically what we have is 10D squared minus 0.4606 D. That would actually be plus equals 0.1125. Now I'm going to bring that over. So I get that 10D squared plus 0.4606 D minus 0.1125 is equal to 0. And now what I do, I use the quadratic formula, right? D is equal to negative B plus or minus the square root, B squared minus 4AC all over 2A, where A is equal to 10, B is 0.4606, and C is negative 0.1125. Okay. So what I can do is solve this thing. So D is going to be negative 0.4606 plus or minus square root of 0.4606 squared minus 4 times 10 times negative 0.1125 all over 2 times 10. So that's negative 0.4606 plus or minus the square root of 0.212 plus 4.52, I am rounding a little bit, divided by 20. That's going to be negative 0.4606 plus or minus the square root of 4.732 over 20. That's going to be negative 0.4606 plus or minus 2.175 all over 20, which is equal to negative 0.0231 plus or minus 0.109. Now, what I want to say is I got to figure out whether it's plus or minus, right? Because the mass can go on either side of equilibrium, go to the left and go to the right. Okay, but we're talking about it going to the right. because we're talking about being pulled. So D must be greater than 0 because it's pulled to the right, which is positive. So then if that's the case, basically I know that D is going to be negative 0.0231 plus 0.109. That's the only way it's going to be positive. And that's going to be equal to 0.0859. So what I can say is the answer D is going to be 0.0859 meters or 8.59 centimeters. In this case, that's how far the spring will stretch before coming to a stop and then heading back the other direction. So that's that problem. Now, the one thing I want to do is I want to just point out a couple little things about this, and then that'll be the end of this particular lecture. So just give me a second here. Okay, so I wanted to show you a cool way to use calculus to derive the work-kinetic energy theorem. Okay, and you can do that with varying forces. So derive the work-kinetic energy theorem using variable forces. And this is again where calculus comes in, right? So you guys probably won't use a lot of calculus, but I figure I'll show you this because there are some of you that like math at this point. And those of you that if you go on to be physics majors ever, right, this is something you'll see it'll become easily done for you. So here we have XF from XI. What I'm going to do is I'm going to plug in what F is. It's MA dx. Now, how do I do that? Because remember, A is equal to dV dt, which is equal to dV dx times dx dt. See, I can take a derivative and I can change it like a fraction. And so notice the dx is canceled to give me the dV dt, but I want a dx because I think the dx might be more helpful. So what I have then is when I do that, I have dV dx, but dx dt is just equal to v, right? This definition of v. So now what I have is an alternative definition for acceleration. It's v dV dx. So let's plug that into the integral. So we know that work is the integral from xi to xf of m a dx, which will be the integral from xi to xf m times v dV dx times dx. Now the beauty of this is look what happens. Because you can treat differentials like fractions, it goes away and I've eliminated the x altogether. So now I'm left with the integral from xi to xf mv dv. Now I can't do x's anymore, right? So what happens is there's no more x, so it goes to v, because v is my new variable, and you can just switch it up like that. So I'm going to pull the m out and rewrite my variable. It's now vi and vf, v dv. Well, the integral of v dv is equal to v squared over 2 from vi to vf. Right. That's m times vf squared over 2 minus vi squared over 2, which is equal to just 1/2 mvf squared minus 1/2 mvi squared. Look at how pretty that is. The expression just pops out. So you get that w is 1/2 mvf squared minus 1/2 mvi squared, which is equal to kf minus ki. So we would call that a derivation. So you put QED after derivation, that stands for Quinn's excellent derivation. It's actually not what it stands for, but it's something that is Latin. And I don't remember what it is in Latin, but it's an expression letting everyone know that you're done. So I just want to talk a little bit further about what happens when I change the path, right? So I can do any path. So what would happen if you change the path and you use the dot product? So when you do that, it's pretty simple. You can use work to talk about any force or any path. So we were dealing with different forces, right? Well, basically what you would do is work would be the integral of f dot ds, right? That would be as your path is changing, right? And again, this is for multiple dimensions. For one dimension, what you would have is work equals the integral of f dot dx, right? And dx would be your path. So this is a common thing that's done when you're dealing with forces in a variable path. So what we can do is I can just show you kind of what that looks like, just so you have an idea. So let's go to the next page so I can generalize with a few drawings and you can see how it works, right? So what I'm going to do is I'm going to just draw some path, right? So I'm going to have some path here, and let me say what we're going to do. Let's generalize. And again, you won't use this in this class, but I think it's good for you to see it. And those of you that have, a love of mathematics, you'll see why calculus was invented, right? So what you would do is, if you have some path, let's say you're going from P1 to P2, going along a path like this, let's say. So that's any path. And let's suppose that at this position here, right, you have a force going this way. Your force is going that way. And then what's happening? Well, at that moment in path, you're going like this in some direction, DL, that's tangent to the path. Just like you would when we did circular motion, right? Actually, I'm going to delete that, make it a little better. I think it's more like this. So this will be DL, right? So I'll be going tangent to the path, right? And this will be some phi. Well, what I really want to do is I got to break that force up, right? Because that force is an angle. So what I want to do is I want to break the force up into a piece here that's parallel or perpendicular to the path. And then here, there's a piece that's parallel to the path. And the reason I want to do that is because the perpendicular force doesn't do anything, right? Only the parallel force portion is going to do anything on the path, right? So let me write that down. So just summarizing what we did, right? We break it up into pieces, parallel and perpendicular to that particular location. And so what happens is the perpendicular piece, again, does no work on the object. It's wasted. The parallel piece is the one that's doing all the work. So what we want to do is let's look at the work done by the force on the infinitely small path displacement dl. So I want to know what the force does over that infinitely small displacement, right? Because that's how I know what to do. So I'm going to come up with this variable dw. That's going to be small amount of work done by the force during displacement dl. What I want you to get used to is the language, right? Amount of work done during displacement, okay? And so how would I get that? Well, it's pretty easy. Use the same formulas. Just because they're differential doesn't matter. dw is going to be f operating on that little path change dl. And that's equal to f dl cosine of theta, right? And again, my angle is phi, so f dl cosine of phi is what it should be called, okay? Once you do that, then what you do is you add up all the infinitely small pieces of work EW along the entire curve. Right? So you just add all of them up. Well, what we do is we add them all up. How do we add something up that's infinitely small? We use an integral, right? Integral dw is going to be the integral f dot dl. Okay. So again, this is just another way of showing you that for any path, when you integrate that, you get the work. The integral dw is w is the integral from points p1 to p2. So your integral gets more complicated. We're not going to get into that because you're not going to do this. I'm just giving you an exposure to how it works. That's going to be delta k, which is kf minus ki. All right, so you have a generalized expression. And if you were to take an upper level mechanics class, this is when you start to use your vector calculus to deal with these curves that are changing. So that basically does it for work. What I want to do, just go over with you quickly, is something called power. Just so you have an idea what it is. Power is important. I mean, we talk about it, horsepower and stuff of that nature. So I just want to make sure that you understand. So I'm going to go to one more slide and we'll talk about power. Now, we're going to talk about this in a physics term, right? Not power of like if you're in charge. So half joking. So, all right, let me give you a couple pointers about this. Okay, so I'm talking about power. Basically, we have to start by, again, just looking at work. So work tells us the amount of energy that's basically used by a force. So for example, if I'm pulling this block and I pull this block 3 meters, right? I can say that I use 10 joules of energy to move a block 3 meters. And that's the work that I'm doing in moving the block. But there's multiple ways you can do this, but suppose I do this 2 different ways. So suppose that I move the block over a 5-minute period of time. So it takes 5 minutes to move the block 3 meters. But then I'm really slow. And over a second period of time of 5 hours, I move it its next 3 meters. So there's clearly a difference, right? Because it's taking me more time to move it with option 2 than with option 1. So it would be interesting to be able to bring in the amount of time needed to do the work. You could almost look at that as like an efficiency, right? Clearly, I was much more efficient in the 5-minute period than it was in the 5-hour period. So we want to find a way to bring in time into this situation. So this is where I'm going to define a variable, a new variable called power. So our new variable power is basically going to be the time rate at which work is done. All right. Now, the other thing I want to note too is, again, you're looking at it's almost like an efficiency, right? So power is going to be scalar. It doesn't matter what direction you're going. So power is a scalar quantity. Now, I also want to define the average power. So the average power is going to be defined as the average work done over some time period. So if I want to write that, I would simply write it as P average is going to be the change in work over the change in time, or you could look at it as work over time. But what we can do from here is we can also define an instantaneous power, right? You want to know the power at each instant as you're moving along, right? Well, in doing that, how would you do that? Well, power, that instantaneous power is going to be the limit as delta t goes to 0 of delta w over delta t. And I don't know what that looks like to you, but I would say that looks pretty much like a derivative, dw dt. So power instantaneously will be dw dt. Oops. Now, again, we won't be using the derivative a lot. That's more for upper level physics stuff, but we do a power calculation. It usually is with an interval. I'm not going to say not ever. Well, let's look at power, right? So power is going to have units of joules per second. Well, it turns out that we define a new unit. 1 watt is going to be 1 joule per second. Okay, or 1 joule second, right? It's another way of writing it. Okay, so 1 watt. Now here it can get confusing, defined with a W. That's also defined as the SI unit of power. Okay. Now let's just talk about some of these things, right? Because power is existent, especially with cars and stuff. It's existent in British units still here in the United States. So just to give you an idea, what we would use is, right, power, the unit, would be 1 foot-pound per second, or more commonly, you would use horsepower, which is HP. Now, where did it come from? It probably literally came from like the power that a horse had. But here's just some of the, here's a couple conversions. 1 horsepower is equal to 550 foot-pounds per second. All right, so if you wanted to convert your horsepower from foot-pounds, that's how you do it. More likely than not, though, you'd want to convert to SI units, right? Because that would be more appropriate. So convert to SI units. What you would do is you would say that 1 horsepower is equal to 746 watts. So this is a unit conversion that would be useful. So if your car was 500 horsepower, you would know what your car would be in watts just by multiplying, okay? Some other common we have some common decimal conversions. A lot of little formulas for power. We use the kilowatt, which is 1,000 watts. We also use the megawatt, which is equal to 1,000,000 watts. We also have the gigawatt, which is equal to 1,000,000,000 watts. So these are just some, conversion factors that might be useful when dealing with power units. Now, where is power most common, right? Or where is the watt most commonly used? The watt's used with electricity. I mean, you look at your electric bulbs, right? Electric bulbs are measured in watts. So just a couple pointers about this. So an example of the watt where it's most commonly used with your electric power is with the bulb. So what does the wattage of a bulb mean? Well, for example, if you have a 100-watt bulb, that converts 100 joules of energy to light and heat every second. So that's what the 100 watts is telling you. It's telling you the energy per second that the bulb is producing, and most of it light and some heat. Actually, the more light, the better. So you could rate light bulbs in horsepower, right? But that's not common. It's not practical. They'd be really weird numbers, right? You'd have fractions of numbers. So we choose not to do that. Now, we can define a new unit of energy that uses work and power together. And this is one you should all be familiar with, I assume, if you pay your electric bill, is we have something called the kilowatt hour. And the kilowatt hour is what your electricity is measured with. If you look at your PP&L bill or whatever electric company you have, right, it'll tell you how many kilowatt hours you use. So that's the unit that's used to measure electric energy. So the kilowatt hour is defined as the work that's done in 1 hour if you have the power of 1 kilowatt. So we can actually determine what that is in joules, right? You know that power is equal to basically your work over your change in time, right? So we can say that your work is going to be power times your change in time. Well, we know the power is going to be 1,000 watts. And we know that the time is going to be 3,600 seconds, right? Because that is that's the unit, 3,600 seconds is 1 hour. Well, that's equal to 3.6 times 10 to the 6 joules. So what you can say is 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules, or 3.6 megajoules. So next time you look at your electric bill, you can actually calculate exactly how much energy you're using each month. So this would be the way you would do that using this conversion factor. Now, one last thing I want to do with power before we do a couple examples is that, you can convert. I shouldn't say you can convert. You can express power in terms of a force and velocity. So again, when you're dealing with mechanical energy, right, you know the force is something, you know how fast it's moving. So it might be more helpful to do that. So again, let's take our average. Our average power was equal to, we said, the work over the change in time. Work, change in work. Well, work is equal to F dot delta S over delta T. And what I do is I'll just move my fraction over. That's F dotted with delta S over delta T, right? So what do I do? Well, I don't want the average power. I want the power, which is the limit. Delta T goes to 0 of my average power. So that's the limit as delta t goes to 0 of F dot delta S over delta t, right? And actually, I should get rid of that fraction because I did that already. Let's just change that. It's F dot delta S over delta t. Okay. Well, that limit's going to be F dot ds dt, which is just basically equal to your velocity v. So another formula you can use is power is equal to F dot v. And notice it still gives you a scalar, right? So just more proof that power is a scalar. So what I want to do is I just want to do a couple example problems just so you get a feel for working with power. So I'll do that now. So here's an example, right? We have each of 2 jet engines on a Boeing 767 develops a forward force of 197,000 newtons. When the airplane's flying at 250,000 meters per second, not 250,000, just 250 meters per second, what horsepower does each engine have? So clearly, right, in this result, we have force and we have velocity. So somehow we're going to use P as F dot V. Okay. Well, if you look at the plane, right, when the plane's going forward, if I do a force diagram of the plane, here's my mass. Well, it should be pretty clear that basically the force is pushing it forward and there's some velocity that you're moving. So in this case, right, phi is going to be 0 degrees and the cosine of phi is going to equal 1. So what'll happen is you'll have the power is F dot V, which is FV, the cosine of phi, which is FV, the cosine of 0 degrees, which is just FV. So for this particular problem, we're going to use power is equal to FV. So then what we're going to do is, we're going to take this engine, right? And we're going to say, okay, the power is simply going to equal 197,000 times 250. Well, that's going to be 4.925 times 10 to the 7 watts. That's really huge, but they want it in horsepower anyway. So we know that that times 1 horsepower divided by 746 watts, right? My conversion factor, we know the watts goes away. So I'm going to get 4.925 times 10 to the 7th divided by 746. Now that'll all be in horsepower. So that gives me 660,000 horsepower for the 2 engines. Well, it wants to know what each engine gets, right? So if I want to know what each engine gets, I got to divide by 2. So then for each engine, it just has 33,000 horsepower, which is a lot. Like your sports cars, like the Dodge Challenger with the Hellcat, which is a really big sports car, right? That's only got 500 horsepower. So you can imagine what a jet engine is like, okay? So what I want to do is I want to do one more example, and then you should be able to do all your homework related to kinetic energy and work. So, okay, so as part of a charity drive, a Chicago Marathon runner with a mass of 50 kilograms runs up the stairs to the top of what used to be called the Sears Tower. I don't know what it's called now, but it's 443 meters tall. In order to lift herself up in 15 minutes, what must her average power be in watts, kilowatts, and horsepower? So really what she has to do is she has to do the work to overcome gravity, right? She's going up and the only force acting on her is gravity. So what we need to do is her work is going to be the work due to gravity, or the magnitude of the work due to gravity, right? And that's going to be the magnitude of FG dot delta Y. Okay, well, that's just FG delta Y cosine of phi, right? Now, what you're seeing is basically if you look at a force diagram of what's going on here, right? I'm going to do it over here, but here's her mass, right? She's moving up delta Y. Gravity's trying to pull her down. So she's winning, but gravity's losing. But again, the degree between them is going to be 180 degrees, right? So the cosine of phi is going to be -1. But again, I'm dealing with power, and I'm dealing with hers, not what's going on with gravity. She's doing what gravity's going opposite gravity. So if we look at this, right, it's basically going to be mg delta y times -1, but that's just mg delta y. Okay, so we know what that is. The work is going to be 50 is her weight, 9.81 is gravity, and 443 is the height of the Sears Tower. So when you multiply that together, that is 217,000 joules. Now, I want to get the power, right? So we know power is going to be the work over delta T, right? Well, I need it. Delta T is going to be 15 minutes, right? And that's going to be multiplied by 60, because there's 60 seconds in 1 minute. Those will cancel. You'll get 15 times 60 seconds, which is going to be 900 seconds. So she wants to do this in 900 seconds. Well, my power then is simply going to be 217,000 joules divided by 900 seconds. Okay. When you get that, 2,002, well, that's big. 217,000 divided by 900, that's going to be 214 watts. Joule second, which is 214 watts. Let's do it that way, right? So there's my first one. I wanted to get it watts. Okay. Now, kilowatts is pretty simple. Power is 241 watts multiplied by 1 kilowatt divided by 1,000 watts, right? We simply get 241 divided by 1,000 kilowatts, 0.241 kilowatts. So my power in kilowatts, and I should put average, I'm being sloppy. So let me do that. Average power is going to be 0.214 kilowatts. Now I understand a lot of you can probably do this in your head, and that's fine, but I like to show all the steps when I'm doing an example. And the third one, right? If the power is 241 watts, I want to go to horsepower. Well, there's 1 horsepower over 746 watts, right? Again, the watts cancel. So what I'm going to have then is 241 divided by 746 horsepower. And I worked that out, that's 0.323 horsepower. So my average power will be 0.323 horsepower. All right, so this is all the problems that I've got for you as far as power goes, but you now have a good jump on, actually you'll be able to do any of the homework they've given you for work and energy, right? So the next thing you'll do is when you finish that is you'll go on to look at potential energy and conservation of energy, which is the next chapter.